Hello, so welcome back to the class. Um, so today we're gonna continue discussion on the electromagnetic wave, and yes, it should be the last video for this one. So I hope that you can finish the video before the our first live chat on Wednesday, right? Yes, it's Wednesday 23rd, I think. Okay, so let's try to finish that, finish this video, this one and the previous one before the class. Okay, let's continue from the last discussions. So just review. So when we start to have discuss about electromagnetic plane wave, so I say that, okay, I assume that we have the E field and the B field, okay? We try to prove the relation between them. And in addition, since this is the electromagnetic, so it should follow the Maxwell equations, right? So what we try to prove is that this E and B following the Gauss law, okay, in the free space. So there are no free charge and then there are no currents, okay? So we prove that integrate of E dot dA is equal to 0 and integrate of B dot dA equals to 0, that these statements are true, okay? And the key point that we are using is that since this should be true for all arbitrary surface, so whatever the surface you draw, this law should be true, okay? So we cannot prove all the surface, all possible surface. So what we do is that we try to prove that if this is true for the infinitesimal surface, so infinitesimal is a very tiny ideal situations, okay? And so we what we do is that we basically assume that the smallest surface we are talking about, this tiny one, is a box, okay? And then if you would like to form any shape, any volume, you can draw it up from the box, okay? And then we use the box to prove the Gauss law, okay? And then last time we stop at the Faraday and Maxwell, okay? And we said that, okay, now we want to prove the loop instead of the box, okay? So, and the principle is the same. So if the statement is true for the infinitesimal loop, it's going to be true for any loop, because you can draw any loop from the small loops, okay? But since we are talking about the loop that lying on the plane in three dimensions, so we break it into three components, okay? So the loop on the xy plane, okay, the loop on the xz plane, and the loop on the yz plane. Okay. So then we can prove the statement for each loop, okay, and then we can see the relation between the equations. Okay, so let's start. So as before, we assume the E field and the B field. So E is in the k directions of EC, which is a function of y and t, and B is bx in x direction as a function of y and t, okay? So now we trying to do the line integrals, okay? I start with the xz plane. I give you just 30 seconds. Think about these two equations and what should we let's say what we get immediately after the after you see it, okay? So what exactly that you see is basically on the right hand side of the equation, the phi b, it's basically integrate of the b dot dA, right? The phi e, it's the same, it's a flux, so it's electric flux and the magnetic flux, right? So the change of magnetic flux create the E field, the change of the electric flux create the B field. Okay. So the direction of the dA is basically, if you have the surface, the direction of dA is perpendicular to the surface, right? So in these situations, so you have the direction of the XC plane in this way, in this direction, right? So this is the dA in our situation. Okay. Then you can see almost immediately that they should not have the magnetic flux and the electric flux. Why? Because the E field and the B field, it's perpendicular to the vector of the plane, right? So E is perpendicular to the vector of the plane, and also B is perpendicular to the vector of the plane. Okay, so E dot dA and equals 0, right? Because E dot dA is basically the size of E dot dA is the size of the E, the size of the dA, and the cosine theta. So theta is the angle between E and dA, which is 90 degrees. Okay, so cosine pi over 2 is 0. This is the same, so B dot dA equal to 0. Okay, so on the right hand side of both equation becomes 0. Next, we're talking about on the left hand side. Okay, I will do it on this one. So let's say that you have the loop like this. Okay, so for the E dot ds on the surface 1, 2, 3, and 4. So basically E dot ds is E dot ds of the surface 1 plus E dot ds of surface 2 plus E dot ds of surface 3 plus E dot ds of surface 4, right? And then you can see that since E is in this direction, so it's perpendicular to the ds of the surface 2 and the surface 4, right? So you have the plane, this is a plane, okay? And then you have the E like this. So in this surface and in this surface is perpendicular to each other, okay? So this thing becomes 0, right? And then E dot ds of the surface 1, it's basically if we don't care about the size, but just looking for the dot product, so you can have like k dot k, right? E is in the k direction, the surface 1 ds is also in the k directions. But for surface 3, you can have E, which is in k directions, dot for surface 3, the ds is in the minus k directions. Okay, so these two terms cancel. Okay, the size is exactly the same, right? E and ds, but the minus size and plus sign coming from the dot product, which they are cancelled. Okay, so on the left hand side you also get 0. Okay, so which is true, so because on the right it's also 0, so there are no magnetic flux change, no E field. Okay, you can do the same for the B dot ds. Okay, okay, so yeah, so this is the first plane that we consider. So let's try the second plane. In case if the you know, since we are, I mean, when you watch now it's video, so if it's too fast, like you still need to think about that, and you need to calculate, you need to, you know, doing the the equation properly, so you can just pause the video, make it slow, okay, so that you can make sure that you know everything that I'm right on the slide. Okay, so next it's we're gonna consider in the YC plane. Okay, so it's the same. We create a direction of the loop. Okay, but what we have to really be careful in this situation is that in this case is that E is a function of y and t. B is a function of y and t. But in this plane, y is not constant. Okay, in the xc plane, y is constant, right? So there are no changing in y. But in this plane, yc plane, and the next one, xy plane, the y has changed, right? So, okay, we say that this is y, and this is y plus delta y, okay? You can say this is c also, and this is c plus delta c, okay? So this is a loop with the size of the delta c times delta y. Okay? And this is just the general case. If you draw the square loop, the size is going to be the same, but that's, I mean, that is a specific case. We just draw in a general case. Okay, so now we start. I would start from the second equation. Why I start from that? Because it's easier, right? So E, the flux of E integrate of the d dot dA, it's become 0, right? Because E is in this direction, but the dA is in this direction, so it's basically perpendicular, okay? So the dot products become 0. Okay, so we don't really have to think about that, okay? It's falling to the same situation as we learned before. Okay? So we starting from the now we start on the first equation. Let's do the right hand side first. The change of the magnetic flux. Okay. So the change of the magnetic flux, so it's equal to the minus, right, d by dt of phi b. Phi b is b dot dA. B is a function of y and t. Okay, so the derivative become the partial derivative because b have depends on y and t. Okay, and then b dot dA. What is dA in this case? Okay, I can write it. So this is I bx y t dot dA, right? dA is this direction, right? This is dA. So it's dot with the size, which is delta y, delta c, direction I. I dot I become 1. And delta y and delta c, you can take it out from the derivative. Okay, so you're gonna get minus dy dc d by dt of the bx. Okay, now we consider on the left hand side. On the left hand side, we can do the same. So it's as before, so we break it b dot ds of the line 1. So this is section 1, section 2, section 3, and the section 4. Okay, plus E dot ds of section 2, E dot ds of section 3, E dot ds of section 4, right? Okay, then which one they become 0? So this is E. So it's perpendicular to the section 2 and the section 4, right? So this thing becomes 0. Okay. E dot ds of the section 1, what is it? So E at the section 1 is K, right? EC. At the section 1, it's y component is y plus the delta y t, right? And okay, dot ds is dot delta y k. Okay, this is section 1. For the section 3 is here. So you get k of EC at y t dot ds is delta y minus k, right? Okay. Then k dot k become 1. So what you have is the delta y, right? And then you have EC of y just a second. No, I think I tried it. Sorry. The s we integrate over the we integrate over the c direction, so it should be the delta c. I'm sorry, k. The delta c of minus k. Okay. Then what you have is delta c. Okay, y plus the delta y minus EC of y. Okay. This form looks familiar, right? This is a form that we think about the definition of the derivative, right? The d by dx of fx equal to the limits when delta x becomes 0, fx plus delta x minus fx divided by x. Okay. So this function should be like the delta x times the derivative. Okay. So you get delta c, delta y, derivative, right, with respect to c. No, sorry, derivative with respect to y, because you divide here, right? Derivative with respect to y, EC. Okay. Then you move the equation here, which is equal to this equation. So equal to the minus delta y delta c d by dt of bx. So you cancel delta y and delta c. Okay. So what you have at the end is that d by dy of EC equal to the minus d by dt of bx. Okay. So now you have first equations. Okay. So now you have that you have the not correlation, the relation between the EC, so the E field in the C direction and the B field in the X directions, that d by dy of EC equal to d minus d by dt of Bx. So this your E and B need to satisfy this condition, because if it satisfies this condition, it satisfies this integral form. Okay. Hope that you can follow. Okay, so we can do exactly the same, okay, on the xy plane. Okay. So on the xy plane, we do the same. So we draw the loop. Okay, we consider that this is the position at y, this is position at dy plus the delta y. Okay, and this is the size of the delta x, and this is the size of the delta y. Okay, so we do the same. So if we do quick, we see that the flux of the B, the chance of the flux of the V, it's become 0, right? Because B field is in the same as a plane, right? In the same direction of the plane. So it's not perpendicular, so there's no flux happen here. So we don't need to think about that. We do it on we do only the integral of the B dot ds minus equal to the mu 0 epsilon 0 d by dt of the E of flux E. Okay. So we I think we start the same. So if I start from the left hand side, okay, so it's become B dot ds in the region 1 plus B dot ds on the region 2 plus B dot ds in the region 3 plus B dot ds in the region 4. Okay, and then you consider that which region should be 0. On the right hand side, what is the flux of E? So it's E dot dA, right? So it's E, which is in this direction. So it's K EC, right? Dot dA. dA is the size, which is the delta X, delta Y in the K direction. Okay. So on the right hand side, you're gonna get mu 0 epsilon 0 delta X delta Y d by dt of EC. Okay, so now you have everything. Okay. Maybe I should write the section, right? 1, 2, 3, and 4. Okay. So I would leave this to you. Try to finish that, but I think you can see it quickly that B is perpendicular to the section 2 and 4, so that you can just cancel that, so that you integral only on the section 1 and 3, and this thing follow what we have done before. Okay, so I leave you to practice on this. At the end, what we're gonna get is that if you do it correctly, you're gonna get d by dy of the Bx equal to the minus epsilon 0 mu 0 dEc by dt. Okay. So this is another equation we get. Okay. So in summary, what we have is basically we have two equations coming from the that we proved before. So d by dy of EC equal to the minus time derivative of bx, and the derivative of bx equal by dy equal to the minus mu 0 epsilon 0, the time derivative of the EC. Okay. Then we try to combine it. So what we can do is that we take the another derivative of y to the first equation. Okay. So when you take the time the y derivative of the first equation, so you're gonna get the second derivative. Okay. And then minus derivative of y, and then derivative of c of bx, right? But from this derivative, you have learned before in the calculus class that if you do two derivatives, so you can do which one first is okay. You're gonna get the same result. So what you have is basically it's the same as you do d by dt of d by dy of the bx. Okay. And then you can see that the d by dy of bx, it's basically this equation, right? So you just plug it here. Okay. So it's become minus times the minus become plus mu 0 epsilon 0 second derivative with respect to c. Second derivative of EC with respect to time. Okay. So you write it down, everything you have. If you prefer on the right hand side, or you just move to be minus on the left hand side, it's okay. Okay. Then you have that. Okay, and you see that this is the form of the wave equation, right? And you also know that if this is the wave equation, this term become 1 over v squared, okay? Or v equal to the 1 over square root of the epsilon 0 mu 0. Okay. So if you find if you calculate this value, okay, so epsilon 0 you get from the Coulomb constants, right? Coulomb, you have the Coulomb constant 4 pi epsilon 0, it's 9 times 10 to the 9 Newton over m square c charge square. And then for the mu 0, you have mu 0 over 4 pi, which equal to the 10 minus 7 m over m bar, like this. Okay. You put everything together, calculate this one. You're gonna get that this v is roughly 3 times 10 to the 8 meters per seconds, which it's the speed of light, right? Okay, you prove the speed of light from whatever experiments, not this one, but this one show that the v you get, it's basically the same as the speed of light. So from this thing, we can believe that this E field, and if you do in a different way, so you take care for the second derivative of the bx over y, and then you change the right hand side instead. So E field and B field follow the wave equation, and it has the speed of the light. Okay, so that is what we know. We cannot really summarize now that it's the light, okay, because it's just that you have something that travel at the speed of light, but it's can be light or it can be something else also, right? This is the um, the conclusion from that. Okay, so if you confuse, so what I'm trying to say is that, for example, you say that the bus is traveling with some speed, but if you can run with the same speed as the bus, it doesn't mean that you are bus, right? You are human. Bus is bus. So so the proof of that, the proof that the speed is the same, it doesn't mean that it's going to be the same thing. Okay. Okay, so now we know that E and B are the wave. Okay, what is the general solution of the wave that we have learned before, right? We already reviewed that. The general solution of the wave, we go back, this one, right? If you are talking about the wave, it's any function that written in the x minus vt or y minus vt if it's traveling in y direction, which is fine, okay? Or c minus vt if it's c plus and minus vt if it's traveling in c or minus c directions. So now we know that this is wave. Okay, so what we try to do is that we will write E in form of the wave. Okay, before we just write E not in form of the wave, but we write E in a general form, right? Y and T. Okay, so now we know that this is the wave, so we can write this one as a wave. Okay, so instead of yt, we write it in y minus vt, for example. Or it's traveling with the speed of light, so y minus ct. Okay. Okay, so this is the first part. The second part, the slide is already it's already on the page, so you can download that. Okay, this is the second part slide. Okay, so for the second part, so continue. We write E and B in terms of the wave. Okay, but you may wonder that is this a wave because it's different than what we are talking about. Right? We say that the general form of the wave is y minus ct. Okay, before it's x because it's traveling in x direction, but this thing we're traveling in y direction, so it's y minus ct. But this is not. This is ky minus omega t. Is it a wave? Yeah, this is we're gonna prove it. Okay, but for now we just assume this one, and then we're gonna prove the relation, and after that you will see that this is a wave. Okay. Okay, let's try to do that. So we put the waveform to the equation that we get before. Okay, so dy dEc by dy equal to the minus dBx by dt. This is the first condition we get, and then the second one, dBx by dy equal to the minus mu 0 epsilon 0 dEc by dt. Okay. So we do the derivative. So we first dip. Just to mention that now we are talking about the side. Okay, we are not talking about the E as a vector. Okay, so the EC is basically this term, and the BX is this term. Okay, so differentiate with respect to y, what you get is E0 differentiate psi is cosine, right? Ky minus omega t, and then you get k equal to the minus b0 cosine ky minus omega t, and then you have the minus omega, right? Minus and minus become 1. Then you can cancel cosine ky minus omega t. Sorry, give me a second. Okay, let's continue. So you have you can write b in terms of b, so e0 become omega over k of b0. Okay. So now we do the second equation. Okay, so differentiate that. So differentiate bx with respect to y equal to the k. I'm sorry, I just do quick differentiation. So ky minus omega t. Okay. On the another side, you have the minus mu 0 epsilon 0 with respect to t, so you're gonna have plus omega. I just do it quick. E0 cosine ky minus the omega t. Okay. If you don't follow, try to do it step by step. You differentiate the overall function and then you differentiate the path of the functions. You cancel this one. Okay. So now you have E0, it's become, right, K over omega 1 over mu 0 epsilon 0 E0 B0, right? Okay. You can make it a little shorter if you go back to the this equation. So you know that C is equal to the 1 over square root of the epsilon 0 mu 0, right? So you put it here, so it's become C square. Okay, so you can just write it on the same line. It's become K over omega B0 C square. Okay. Okay, so now you balance it, right? These two equations, they are equal, right? Because basically it's the same E. You have E0 equal to this term, and then you have the E0 equal to this term. So basically these two things, these two boxes are equal, right? So what you have at the end is that when you try to equal that, it's omega over k of B0 equal to the k over omega B0 C square. So you cancel B0. So what you have is omega over k equal to C, right? This is correct? Yeah. You get the omega square over k square equal to C square. Then you square root of that. So omega over k equal to C. Okay. So from this one, it's following the consequence, you put it back to the first one that you get. So you get E0 equal to the B0 C. Okay. So now you have the relation of E and B. Okay. you have the relation of E and B, and you know that the omega over k gonna become the speed c. Okay. So now you see that E and B is basically the same thing in the, let's say, in the matter of the size. So you have, if you have the E, it's control the size of the B. Okay, it's just going in the different directions. In this case, E it's propagating in the k directions, in the c directions, where YB is propagating in the x directions. Okay, and then it's oscillate, in the same way because you have the same function psi ky minus omega t. Okay, so at exactly the same place and same time, the psi term gonna be the same. The difference is just the magnitude of B and B, which is different. Okay, but when the psi becomes 0, it means that E becomes 0 and B also becomes 0. Okay, get me? Okay, if you get that, so you can draw this thing. Okay, so E and B it's propagated in the same way, just different directions, and when it becomes 0, it's 0 in both components. Okay. So first we talked that we should say first that is this still a wave or not? You see that this is a wave, right? But if you still wonder that is this a really wave, so you can do E from, for example, from E. You say that if this is K E0 of psi, and then you put the K out of the bracket, get Y minus omega over k t, right? And the omega over k is basically c. So you can see that this is a function of y minus ct, right? This is the wave form. Okay. So clearly this thing follow the wave equation, and this thing also follow the wave equations. Okay, this thing and this thing. So this is the wave. We already know that. Everything that we apply to the wave before, we can apply here. Okay. For examples, the wave can behave the same when you repeating, right? When it's traveling, when the let's say the distance become lambda, so the wavelength. Okay, so this is the wavelength lambda. Okay, so what is lambda? So you have the equation of the ky, right? It's k lambda equal to the 2 pi, right? So every 2 pi, the waveform gonna be repeat. Okay. So you get k equal to the 2 pi over lambda. And this is, you also get it from the mechanical wave. Okay, and k represent it's called the wave number. Okay, so the wave number is the amount of the wave that you have. So this k represent that, for example, if you have a string and you have the wave with the wavelength lambda, so the k tell you how many wave that you have in 2 pi length. Okay, this is the k. This is how the k represent. Okay, how many wave. In 2 pi, right? Okay. And then you also have that, you also know that when the wave also repeats, okay, when the time period equal to the, when the time equal to the period, so the omega t equal to the 2 pi, okay, then you get the omega, which is the angular frequency, it's equal to the 2 pi over t, where t is the periods, okay, or it's equal to the 2 pi f. Okay, so this what we know. And then And the last thing that we see from this equation is that the wave propagation direction follow E cross B, right? So you have E, you have B, so it's following the right hand rule. Okay. Just in case we're gonna use this word later. So the word of the polarization, it's basically the propagation direction of E. Okay, it's the E direction. This we don't use it now, but just tell you that when we talk about the polarization, we say we're talking about the direction of the E. And if you would like to know the direction of the B, it's fine. It's need to perpendicular for that. And if you know the direction of propagation, you can reverse engineer back to the direction of the B. Okay. Okay, so this is the wave. So in the electromagnetic wave, you have the range, wide range of the frequency. Okay, so it's covers several things. So if you looking on the spectrum of the electromagnetic wave, so what you're familiar with is the visible, because this is the light that you see. Okay, the rainbow that coming out from the prism when you put the white light through the prism, right? So this is what you know. You have the infrared regions, and then go to the microwave and radio. So this range used for the communication. Okay, the infrared is responsible for the heat, like when you when you feel hot because of the sun, that's because of the you can sense the infrared that's sent out from the sun. Okay, so you have UV, you have the X-ray and gamma. This is several applications, including the X-ray machine, right, for the medical, for the industry. Okay, and then what you also know that let's say that we can sense the wave in a very limited wavelength. Okay, so for human, we are sensible for the visible light because we can see the light. Okay, we may be sensed for the infrared because we can feel hot. Okay, but we may not sense something else if it's not really affect to us. Okay, so what the machine that we are making, it's basically sensitive to the which region. Okay, for example, if you making the antenna, it's sensitive to the radio or microwave region, for example. Okay, some animals, they have let's say the different organs that sense to the different thing. For example, snakes. Okay, when you maybe see the news that snake bite people or animals in the night, it doesn't mean that it can see with the visible light in the night, because the visible light in the night, it's dark, you don't have light. Okay, but the snake have the organs that sense to the infrared, so that it can use that one to as a direction to go to the living things. Okay, because us or any living things can radiate, so that radiation is infrared, and that the snake can sense that. It's also the range of the electromagnetic spectrums can help us also to see universe in a different way. Okay, when you're looking on the photos of the universe taking from the space station, for example, or satellite or telescope, normally we take in the different wavelength. Okay, so that you see it different, and then that's composed together, how things is formed or what is the structure of that. So you have like maybe you already know the Hubble telescope, which I think retired already, the Spitzer. So both of them sense in a different region. Sorry, they are sensitive in a different region. So the Spitzer it's sensitive in the infrared regions, while the Hubble it's covering the UV, the visible light, and the infrared regions. Okay. And then the next one that maybe you see the news of the James Webb Space Telescope, right? In the last month, that it just sent out to the space already. So it's cover the end of the visible light to the far infrared. Okay. So this is the spectrum of the electromagnetic wave that have the different application on them. Okay. Next topics. When you're talking about the wave, as you learn from the mechanical wave, so in that time, we start with how the wave is formed, right? You disturb the systems, and then the system start to vibrate, and that's a wave. Then we discuss about the property of the wave, right? And after that, we say that the wave is basically it can transfer the energies, okay? But for electromagnetic wave, we didn't really discuss about the source of the electromagnetic wave, so it's not in the course syllabus of our course. Okay, so I will not talking about that. I mean, maybe I will just say that it's coming from the oscillation of the charge. Okay, so when the charge oscillates, basically, like you have the capacitor, and then you connect it to the alternative source, alternative electrical source, for examples, so that the charge can switch. Okay, so the polarity of the pole can switch, and when it switch, what is changing is the flux is changing, right? So when the flux E flux is changing, it's create the B field. Okay, and together with the E field and B field together, it's formed the electromagnetic wave. So that is the simple way we describe about the electromagnetic wave. Okay, in the survey, there is a section of the antenna. So it's basically there are no calculation on that. Just tell you that how the antenna works. Okay, basically, so you can read it by yourself. But we go to the one of the important topic about the wave that you should learn. It's about the energy carried by the electromagnetic wave. Okay. In these sections, we will not invent something new. I mean, from scratch. We're gonna use what we have learned before. Okay. So in the time of the first part of the course, you already taught I think you already learned or discussed about the energy. So the energy density, so energy per unit volume that associate to the field. Okay, so I just put the equation here immediately. So if it's associated to the electric field, you get the epsilon 0 E squared over 2. And if it's associated to the magnetic field, it's B0 over 2 mu. Okay. Okay, so this is the definition of the energy per unit volume, okay, of the associated with the fields. If you're not familiar with that, or you cannot, never seen it before, so that you should go back to the course, the course that you have taken for the first part, and looking for these two equations. So we're gonna do a little proof on the energy carried by the electromagnetic wave. We should start from the basic picture of what we are talking about. Okay, the basic picture is that you have the area that you would like to that you put it, and when the wave comes, it gives the energy to this area. Okay, and then the wave come, right? So at this, since the area is fixed, so it's a certain place, but the time move. Okay, so when the time pass, after the wave reach, so the energy is let's say the energy is, sorry, so the wave gives the energy to this area continuously when the time pass. Okay, but if we're talking about at the certain time, okay, the energy that you will that the wave will give to this area, it's what we call the instantaneous energy densities. Okay, so you just use the energy per unit volume associated with electric fields. So you have the energy from the E field equal to the epsilon 0 over 2, right? And this is the wave. So we go back to the wave equations that we have. So E0 psi ky omega minus omega t, right? So you have E0 square psi square ky minus omega t. Okay, and then from the B field, you're gonna get 1 over 2 mu 0 B0 square of psi square ky minus the omega t. Okay, so what you have to do is basically you sum it up, right? Then you get the total energy that deposit, the total instantaneous luminosity that deposit at the regions at a certain time. Okay, so what you have is that go back, you have E equal to B0 C. So if you would like to write in the E form, so you know that B0 equal to E0 over C, right? So from the B field, it's gonna become 1 over 2 mu 0 E0 square divided by C square psi square ky minus the omega t. Okay, and the C square, you know that it's 1 over epsilon 0 mu 0. So mu 0 cancel, E0 move to the nominator. So you have epsilon 0 over 2 E0 square of psi square ky minus the omega t. Okay, so the total energy density becomes 1 plus 2, right? So it's become epsilon 0 E0 square psi square of ky minus the omega t. Okay, so when and then you fix the y if you fix the position, so what change is time. Okay. Then if you would like to have the expected of U total, this is U total. So expectation is 1/2 epsilon 0 E0 square. Okay. Because you integrate 1/2 pi to 2 pi of sine square theta d theta equal to the 1/2. Okay. So now you have the total energy densities that reach the area. Okay. Then we are talking about the concept of the we can starting to talking about the concept of the intensity and the Poynting vector. Just note to you before that when I rearrange the lectures, I didn't really, I follow what we have in the book, okay, in the survey book, but sometimes when I try to prove something, they can prove in a different way, okay. So I start from, I try not to define something from the beginning, but what I try to do is that to follow what we have before and then point you that this is the new thing that we can define, okay. But in the book, sometimes it will define first and then it try to work on that. And if you work from that, you go back to the result that you have before. So this is the same, okay. It's just different way to prove things, okay. So we start we talking about the intensities, okay. The intensity I, okay. Intensity is measured as a power, so it's watt over square meters over the area, okay. I should maybe write area, which is the meter square, okay. And then the power is the energy per second, right? So it's joule per second. So joules is the energy per second. Okay. So if we would like to know the intensity that or the power per unit area that you will get when you get the radiations, okay. So the situation is that you have the area, right? The EM wave come, and then you say that what is the intensity, what is the power per unit area that you will get, okay. So if you looking on the definitions, so you know that the intensity gonna be the energy per area per seconds, right? The area, we can force it, the area to be square meters. Okay, if you have 2 square meters, you just divide it by 2, that's fine. But if you prove in general, you just put A equal to 1, so it's become per square meters already. Then what you have to do is per seconds, right? Per second, what does it mean? It means that when you have the area and then you have the wave come in, pass through it, and after the second, this wave, it's, let's say this plane of the wave, this front, it's traveling for 1 second, okay. So what you would get, the total power per second, is what starting from the time that the wave reach the area and then passing for 1 second, okay. So it's starting from this one and then it start to propagate, okay. It accumulates the energy that released to the area, okay, for 1 second. So the intensities become the total energy, right? That it give you for 1 second. Okay, so the total energies, okay, so the total energies that it gives, it's the average, right, of the U total, and then it's traveling c, right? In 1 second, the wave can propagate with a distance c, right? C in 1 second. Okay, so when the wave reach here, it's give the energies, and then the wave continue. In 1 second, it's reached here, right? And then what the follow this red dot, it's also when it reach, it's release the energy. When it reaches, it's release the energies. Okay, so the energy that's stored in this volume, it's basically the average times the length, and the length is c. Okay, because the wave traveling uh, in the so equal to vt, right? S equal to vt, so with the speed c and t is 1 second, so the length is c. Okay, so what you have is, so this is the average, but if you would like to write it in the general form, so you can do it something like epsilon 0 over 2 E0 square times C psi square ky minus omega t. Okay, this is you write it with the general form, or if you would like to do it as the average and then the average times C, this is the same. You can do that. I mean, it's nothing wrong. Okay, and then you break the component a bit. Okay, so E square, sorry, this I miss any term. Sorry, I should use the total energy, so I should use epsilon 0 E0 square of psi square ky minus omega t and c. Okay, right. Just give me a second, just make sure that I do it correctly. See, it's B psi theta so you check the B here. So yeah, I have the same problem when I write, when I describe it in Thai sections. Did I miss some factors here? Oh, it's just, give me a second. Yeah, I think I got it. Sorry, I just tried to do it quick. So you have E0 equal to the B0C, right? So what you try to do is replacing E0, one of that, not E squared, so you take one of E and write it in the B form. What you're gonna have is, I place the C here, you have the epsilon 0, you have E0, and then you have B0 C multiplied to C, so it's C squared over the psi square ky minus omega t. Okay, and then for C square, you know that the C square become 1 over epsilon 0 mu 0, so this thing cancel. Okay, so finally you have E0 B0 psi square of the ky minus omega t divided by the mu 0. So this is the instantaneous, the intensities. Then we define a new parameters called the Poynting vectors. Okay, the Poynting vector S is defined as the E cross B over mu. Okay, what is exactly the Poynting vector? So you can see that if you take the absolute of S, so it's gonna be E, B, and psi, right? And then you take another size there. So basically this thing equal to the intensity. So this is what it said. So the Poynting vector tell you exactly the energy per unit area per time that the wave give it, the electromagnetic give it to the surface. Okay. So this is the definition of the Poynting vectors. Okay. In survey, they will give you the Poynting vector first and then try to prove that and just do it in different ways. So we start from the concept of the intensities and you try to describe you what intensities calculates, and then I just define the Poynting vector at the end. Okay. So now you have the new parameters, the new variables called the Poynting vectors. Okay. E cross B over mu. Okay. Okay, so let's try to make the application a bit, try to understand what is the Poynting vector is. Okay, so the question is that why is shirtless a bad idea for the outdoor activities? Okay, so this is what this is me. Okay, using this same T-shirt and maybe putting sunglasses. Yeah, so this is to protect the light. It's important. Okay, so what is this poor guy it's talking about? It's about the light can damage your skin, for example. But that's its explanation in the biologies and the medical way. But let's try to do it in physics way. Okay. So you get the light, where the light come from? It come from the sun, right? So assume you have the sun here. Okay. And then the sun radiates, right? The light electromagnetic wave to the earth. Okay, so it's radiated to this poor guy. Okay, with a distance that roughly 150 millions kilometers. Okay, roughly. You don't need to say that this is Thailand, that is some place on a mountain. Fine, because it's ranging is like in the order of a few kilometers, but we are talking about a million of the kilometers. Okay, so the variation doesn't really hurt you much. So what is the energy that sun give it to your bodies? Okay, you can assume that you have the surface area of your body, it's 1 square meter, for example. It can be less, it can be a little bigger, it doesn't matter much. So now we're trying to use the concept of the Poynting vector to calculate this one. So what you need to know is basically the power of the sun, right? What is the energy that released from the sun per second? So the power of the sun so it's the energy per seconds. You can look at it in the internet. So it's 3.9 times 10 to the 26 watt. Okay. Then what you would like to know is basically this is the sun. This is the area we are talking about, right? What is the size, the absolute of the Poynting vector or the intensity that you will get? So the sun is radiates in all direction, right? So we need to talk about the sphere. Okay. So the size of the Poynting vector or the intensity we are talking now, it's basically the power 3.9 times 10 to the 26 watt divided by the all area, right? So this is the area of the sphere. So it's 4 pi times r squared. So 150 million kilometers square, right? Oh, sorry. I should just absorb the kilometers. The 10 to the million 10 to the 6 kilo, it's 10 to the 3, so it's 10 to the 9 square meters. Okay. So you get the intensity roughly 1,400 kilowatts. I'm sorry, watt. Right? You can just, yeah, you 10 to the 18, so it's 10 to the 8, 3.9, 10 to the 8, 10 to the 6, 3.9, yeah, 10 to the 6, 3.9 is up to, oops. Let's say it's roughly 4. So it's 10 to the 10, 20, 10 to the 6, right? So 15 times 15 is 225, 225 times 3.14, it's roughly 700 something. Yeah, 775 something, and 10 to the 6. So you can take 10 to the 3 times 10 to the 3. This is roughly 1.3, 1.4. Okay. So it's 1,400 watts per square meters. Okay. So this is roughly. So this is the intensity when you are outdoors, okay, and nothing protect you. So this, if you compare to the radiation from your body, the radiation from your body, it's you can search on Google. So it's maybe from 100 to 200 watt. Okay. So this is from your metabolisms. So when you radiate something, okay, so what you get is 1400, but what you radiate it's 200, 400 if you biking. So you get a lot of the energies coming from the sun, okay, and that's why it's create a burn, because you cannot really radiate something out from your body, okay. So this is the way that you use physics to explain your daily life, for example. So now you know that it's a bad idea to go shirtless for the outdoor activities for long, right? Because when you talking about the long, you accumulate the time. So when you accumulate the time, every seconds, every half of a second, you get the energy that radiates from the sun. Okay, so this is the bad idea. However, this is not that bad that you learn physics, because you can explain this kind of the problem in the way that not many people try to explain to you. Okay, then we have the last topics. It's almost 1.5 hours already, 1 and 20 minutes. So yeah, let's finish this one. So the last topic is the momentum and the radiation pressures. Basically, we can just start from the definition that we have before. So we're talking about the size of the Poynting vector. If you remember now, it's the energies, right? Transfer. It's the energy transfer per area per time, right? And we know that the energy transfer per area is the power, right? This is power. What is the power? When you learn the mechanics, the power is the differentiate, the change of the work done, right? The power is the change of the work done. Okay, so you can say that this is area 1 over area, the change of the work done. So work done is F dot dx, right? So what you have is F over A times V, right? dx by dt is the velocities. So F over A, this is what we call pressure. I think you learned that from the fluid dynamics, okay? So yeah, so this is a pressure. So the radiation pressures in this sense is equal to the size of the Poynting vector divided by V. Okay. Yep. So this is the definition. Let me check if I follow the book or equations we have. Right. Okay, we have it. Okay. And then in the book, it just said that, okay, you have the surface that totally absorb things, and the surface that have the reflecting perfect reflections, for example. What is the change of the pressures? Okay, but in that case, you know that it's changing of the momentum, because one, it's you have the balls going to the wall, and then ball stick to the wall. So this is one situation, and then you have the wall and the ball go back. So you have the twice of the momentum change, for example. Okay, and then this pressure change in that sense. Okay, I think this is all for the first topic. So let's see what we have learned. Okay, so for the electromagnetic wave, we start from the reviewing of the laws that we have, like the Gauss law, the Faraday's, and then the amperes. And then we're talking about the capacitors and say that the ampere's law cannot really describe the flowing of the currents. So you need to introduce the what we call the displacement currents, which introduced by the Maxwell. And then we have the general form of the ampere's law. This is what we have learned. After that, we're talking about the Maxwell equation. So basically, the form of three laws that we have. Okay. After that, when we have the Maxwell equation, we would like to we start to form the electromagnetic wave. So we assume E and B, and what we have done is basically we try to prove that E and B follow the Maxwell, right? Because the Maxwell equation is the general equation relation between E and B. Okay, so when we prove that, that is the E and B that we assume it's follow that, and E and B also forming the wave. Okay, so that's what we can call, that's what we can form the electromagnetic wave. And then after that, later today, we are talking about the energy carried by the wave, because this is one properties, right? The wave, it's carrying the energy with it. Okay. And then at the last topic, we're talking about the momentum and the radiation pressures. I also tell you about the spectrum of the electromagnetic wave. If you remember the pictures, that we have the range from the X-rays to the visible, to the ultraviolet visible light, infrared, and then microwave, and the radio wave. Okay. We didn't really discuss about the production of the electromagnetic wave by the antenna, but I tell you briefly that the electromagnetic wave can be produced with the oscillating of the charge. So when you oscillate the charge, the flux change, the electric flux change, create the E, and then you have the both E field and B field together. That's from the electromagnetic wave. Okay, but this topic we will not have it in the exam. Okay, it's a topic just to describe how things work. There are no calculation on that. Okay, so it's good to read. Just try to read it if you have time. Okay, then I think we are done with this the first topic of the second half of the class. We're gonna have the live reviews and the exercise on Wednesday of 23rd. So please try to finish the lectures before, and if you still have the questions, just send me an email or drop me a message on the Facebook group. Okay. Okay, so next topic will be the geometric optics. Okay, so we are talking about the light and the property of the light. So reflection, refractions, interference, and the diffractions. Okay, so thanks everyone. Talk to you next time. Bye bye.